Okay, I'm on a little early for the 125 class. Link's been up for a while, and I clicked go button 5 minutes before I planned, but I'm here, and we get stuff to work on, so we'll work on some stuff. And if you join in a little later, we're not really going to notice. So you can drop in questions here anytime if you're looking at review stuff. I'm recommending that you look through the tests that we've taken and make sure you understand the stuff that's on there. I mean, things that you didn't get right the first time, definitely go back and revisit that. But also, even if you did them fine on the test when we took it, you might not remember it now. So you got to refresh your memory on that. Make sure you still know the processes, the sort of procedures that we use on the different things. The earlier algebra stuff, we've done a lot since then. We've done a lot of trig lately, and I want to get back to the earlier algebra stuff, but this last chapter that we're working on gives us a good opportunity to revisit all of the algebraic stuff, because these nonlinear systems can include all kinds of stuff. We're solving equations again. We're starting off with two variables, which is different, but we're working our way down to one variable, and then we have one variable equation, which is exactly the stuff we were working on early in the semester, so we get a chance to put all of that to use. I like how these systems here at the end can really organically bring up a bunch of review of stuff that you did a long time ago and might not remember, with graphs and quadratics. If we try to graph the systems, we can remember how the graphs work. If we just in the process of solving the equations, we use a lot of the equation methodology that we had earlier for quadratics, polynomials. Exponentials and logarithms might show up in some of these problems, and you don't know what you're going to see. So it's good review. It's great for review. So I'm going to work some of those exercises today, and then whatever other questions come along, we'll work on that. I'm going to get situated on this. And we're going to work some systems. See how they work. So I'm going to get this situated.
What the number is. Okay.
So I have some of these from the Lumen work. I was going to take an example from there if I can find this again. From the practice work that's in nonlinear systems section on our Blackboard course. These are practice problems, but this is one of them on the nonlinear system. Starts off like this: x minus 11 squared plus y minus 5 squared equals 50, and x minus 3y equals negative 14. So that second one definitely should look familiar to you. That's a line. That's got an x and a y term. We could put it in y equals mx plus b form or something if we wanted to graph it. It's just a straight line. This one's not. Of course, you got the squared things up here, and you might not recognize this, but that's a circle equation, or it's really the distance from 11 and 5 that comes out to this. This would be the square of the distance. But that's a circle equation. So you got a line and a circle. They might intersect in a couple of different places, and I would kind of expect two different intersections. If a line crosses a circle, it's probably in two different places going in and out. So we'll see what happens. I'm not going to do the graphs of them specifically. I'm not going to sketch the graph, but I am going to solve the system, and I won't be surprised if we get two solutions anyway. Now, adding these things isn't going to do me much good at all, because I don't have like terms here. The squareds are up here, so I'm not going to be able to eliminate stuff by adding it up. It just doesn't line up for that sort of thing. So what comes to mind is using a substitution method, where we isolate one variable and then we have an expression to substitute for it in the other equation. So the easiest thing to get by itself is right here. This can easily be rewritten by adding 3y here to both sides. X equals 3y minus 14. And so I have this expression for x. I can substitute that for x and then just work it out from there into the other equation. So this thing copy that down, but I'm substituting this expression in place of x. So that's 3y minus 14 in place of x. Then I'm gonna have the minus 11 there, so I got to put that together. See what we end up with from that. But whatever it is, it'll be a one variable equation now because I replaced x with this expression. So all I have is y's now. I just got to solve for y, and we'll go from there. I have to remember my solutions to this thing need to be ordered pairs. X and Y. I'm expecting maybe a couple of them, but I need an ordered pair. I'll solve for Y, and then I'll have this to come back to. And once I know what Y is, I can calculate the X that goes with it. So that's no problem. I just got to see what happens with the rest of this equation. So inside the parentheses there, I got 3y minus 25. And I'm going to keep all of this here, and I'm not doing anything with it yet. I guess I want to go ahead and square these things out because I have to combine. I'm going to have like terms, but I have to get them all out where I can deal with them. So I got to get rid of the parentheses now and go ahead and square this out. Y minus 5 times y minus 5 is y squared minus 10y plus 25. And this one, this is 3y minus 25 times 3y minus 25. That's also going to be super long, but I'll write down what we end up with there. That's 150y plus 625. So we're getting some big numbers on that. That's added to the rest of those. So I'm going to combine like terms now. I got 10y squared. I'm probably working way off the screen. It's getting long. 10y squared minus 160y plus 650 equals 50. Now you might not have a category that drops into there, but we got an equation. It's a y squared term and a y term and number terms. That's a quadratic kind of thing. So we want to use quadratic type stuff with it. Maybe a factors. Maybe we can use the quadratic formula. We got techniques for that. But first thing we want to do is get a 0 on one side. So I'm going to subtract the 50 from both of the number terms. I got 10y squared minus 160y plus 600 still equals 0. If you're thinking there's a common factor of 10 there, we could take that out. That's true. That's the first thing to think about with factoring. Is there a GCF there? And there is. So we get a little factoring practice built into this. See how all the different topics come up kind of in the process here. This is a nice chapter to end up on. We're going to have to come back to the original problem, but I'm just going to work my way through on this for a while. I need some space. Heavy shadows on this. I'll try to watch that. That's what we got so far. It might factor, it might not. It does in this case because there's numbers that multiply to 60 and add up to 16. So I get nice factors to the thing. And remember how factoring works. And then how it works in an equation. We have it factored. We're using the zero factor property. If this equals 0, that means either y minus 10 equals 0 or y minus 6 equals 0. So the actual solutions to this are y equals 10, y equals 6. Great. Those are the solutions to this, but we got to go back and get the system solutions. So now I know 10 and 6 are the y values. Right, back to my original system. My ordered pairs are going to have something with a 10, something with a 6. I'm thinking just one of each. Yeah, x equals this. So once I know what 10 is, I'm just going to have one answer for x. Y is 10. That's 30 minus 14 is 16. And if y is 6, that's 18 minus 14 is 4. So that works out to nice numbers. those are things that should come out in both equations. That should work in both equations now. You can check those if you want to, right? If you got 4 and 6, you got negative 7 squared is 49, 1 squared is 1, 49 plus 1 is 50. They're going to work just fine in both equations. Those are your 2 points of intersection if you graphed those things. I'm not going to take the time to graph that one, but we could. Probably graphing is something we did a little bit of, not so much with the circles. I should be able to graph that line if you want. It goes through these 2 points. That's not hard to do. But we don't really need the graph to solve the system if we can follow through the algebraic stuff. It is nice to have a sense of how many answers to expect. But if you remember your algebraic processes, it all works out in the algebra here. Anyhow, let's see about a little variety on these. We're not doing inequalities. So some of these practice problems, we have one section in there that says systems of nonlinear equations and inequalities, and we're not doing the inequalities, so I'm not going down that road. I'm going to do another system here. Y equals x minus 2 and x times y equals 3. We're trying to find 2 numbers that multiply to 3, and one of them is 2 less than the other. I guess that's one way of saying it out loud, but we're going to solve this little system. We need an x and y that make both of these things true. I think there's a fairly obvious solution to that, but I don't know if that's the only solution. And when I say obvious, I mean, to me, the math teacher, it's kind of obvious. It might not just jump out at you, even if it did. You have to wonder with nonlinear systems, do they also intersect somewhere else? What does this thing look like graphically anyway? Y equals x minus 2 is an easy graph. We should remember this stuff. That's slope 1 and intercept negative 2. So that goes through this point and goes over 1, up 1. We're going to have a straight line this way. Well, it's a straight line. It's a diagonal line with slope 1. It looks like that in the xy plane. That's fine. This thing is not in a form you probably recognize for graphing. But if you think of that in y equals form, you have to divide by x. It's 3 divided by x. I think we did 1 over x. Y equals 1 over x, the reciprocal function when we were doing graphs. Multiplying it by 3 would be a stretch of that thing. So it's going to be a version of that reciprocal thing that's undefined when x is 0. Looks like this then. Stretched out version of this graph. Negative when x is negative. Positive when x is positive. Looks like that. Even if you didn't remember those, if you can put them in y equals form, then your calculator can do that. And you can see there is 2 solutions. There's one where x and y are both positive, and there's one where x and y are both negative, evidently. So let's see what happens algebraically to work that out. I'm not going to be able to get rid of anything by adding, because this x times y is multiplied. I don't have the same term up here. I'm not going to be able to eliminate anything. So this looks like another substitution thing. Y is already isolated. So I might as well just use the expression that I got right here, put that in place of y. We're going to substitute that thing. So x times y equals 3, but y is x minus 2. So x times x minus 2 equals 3. That's the logic to it. And then you have to think, what kind of situation do I have here? This is kind of factored, but 2 factors multiplying to 3 doesn't really tell me anything. I got to work it out. I got to get to 0 on one side and see what happens. So go ahead and multiply it out. If I move everything to one side here to get to 0, I do have something that'll factor. Nice about that. You should remember the quadratic formula, but a lot of these exercises are designed so that they factor kind of nice, which is good. Those are the factors of that one. 0 is then either x minus 3 is 0 or x plus 1 is 0. We got to find the solutions. and that's positive 3 or negative 1, which looks right with our graph. But those aren't ordered pairs, right? My answers to these things have to be ordered pairs. If x is 3, then obviously y is going to end up 1. You can do that in either thing here. When x is 3, y is 1. That actually works in both of them. That's what we want to know. So that ordered pair works. If x is negative 1, y is negative 3. And that also works in both of those. They multiply to 3. So those are the ordered pairs that work there. That's solutions to that system. Review topics would be nice. Let me see what we have on that. Definitely wanted to work through a few of those, remind you of some of the algebra stuff because we did that a long time ago. Should do something where that elimination process, that addition process actually does the job, which I haven't done that. I haven't done one today, so I'll work one that comes out that way. When you have nice like terms, you can do it that way, and then maybe we can do some of this practice from the final, just as additional review here. Get used to it. We'll do one that's a linear system, which means I won't have anything fancy showing up in the equations, just x terms and y terms. I'll work on one of those. All right, I'm going to write one down. I don't know the answers to it already, so we'll see what happens. But these are straight lines. These are linear equations, both of them, just x terms and y terms. Both of them are straight lines. Could graph it, not going to take the time now. But being straight lines, I'm not going to get a whole bunch of different intersections. They're probably going to intersect, and that should just be at one point, so it works okay. And I do have like terms. These x terms can be added, and these y terms can be added. Adding them up right now wouldn't do the job. I need to get the opposite terms. So my thought process is to get opposite terms on one of those variables. I don't need that in quotes, but I need to emphasize this is the main idea for this method is these opposite terms. So 7 and 4 are not really friendly to each other. 3 and 1 can be done. I'll make this into 3 and negative 3. So my first equation, I'm just going to keep it like it is. And the second equation, I'm going to multiply by negative 3. Because that gives me a negative 3x. I have to do every term by negative 3. So that's now negative 12y. And that's now negative 54. Yes, yes. So I multiplied everything there by negative 3. This is the same line. It's just written differently now. And I managed to write it in a way that I got opposite terms. Opposite numbers on the x terms. So when I add that, that's going to be gone. 3x plus negative 3x is 0. That doesn't do anything for me. Negative 7y plus negative 12y is negative 19y. And negative 54 plus 6 is negative 48. That does a lot for me because the x is gone. Now I'm down to one variable. And not just a one variable equation, but a very simple one where I can solve for y very easily. That's negative divided by negative, so it comes out positive. 48/19 is the fraction, but we can handle that. That's the y value, the only y value that I got, but I need the ordered pair for this thing again. So I got to go back and find the x that goes with it. My solution so is something, comma, 48/19, x comma y. I know the y, so I can write that down, but I got to come back and get the x that goes with it. Any of these equations that have both variables will do. I'm going to use this x plus 4y equals 18. So if x plus 4y equals 18 and y has to be 48 over 19. Then I can get x by itself in this thing. Kind of clunky numbers, but let's work this out. 4 times that's 4 over 1 times that. So I got 192 over 19. So x is 18 minus 192 over 19. Now I have to subtract that just to get the fraction out of that. It's 18 over 1. I got to make it all into 19ths to do the subtraction. So I'm multiplying by 19 on this one. That's kind of big. 642, I believe. And subtract that out. Subtract 192. I get 150. I'm sorry, I wrote this wrong. 18 times 19 is 342. I don't know where I got the 6 from. 342 minus 192, which is 150. So I got 150 over 19. That's what happens when I just make up problems on the spot. They're going to have an answer, but they're probably not going to be nice numbers like clever little textbook problems. But 150 over 19 is the x value. And that's the only solution to that system. Linear system, generally going to have just one answer to it. It goes through straight line graphs. That's where they intersect. All right, not having any questions to respond to, I'm going to go back to this practice document that I put up. So in Monday's announcement, there was practice problems for the final. Had a bunch of these things. I ended up with some systems on there. So that's good practice. But also a bunch of other things on the other chapters that we've been through. Been a little while since we looked at logarithms and exponentials. So let me work a couple problems from there while I'm on. And then any others there that you have questions about, you can always email me anytime. Watching for that. So I'm working from practice problems. Number 29. Oh, that's a multiple choice. I don't want to do the multiple choice right now. Graph the function. We will graph the function here. Log base 1/3 of x plus 2. That's a weird log because of the weird base on there. We could rewrite it, but we don't need to. For the graph, there's two things to remember with log graphs. The input has to be positive. So we got a domain thing. It says to graph it, and it says to give the domain and range. And I like to do domain first and graph the thing, and then look at the graph and write down what the range is. That's kind of a smart way to approach it. You want to think about what kind of inputs you can have first. And for this one, the input into the log has to be greater than 0. You can only do the log of a positive. So x plus 2 has to be greater than 0. So x is greater than -2, or from -2 to infinity. Doesn't include the -2 because you can't do the log of 0 either. It's from -2 to infinity. We're going to have a asymptote at -2. And then it's going to go on just to the right of that. That's what we're saying. The key points on log graph, whenever I have log base b of x equals y, the key points to it to get going on the graph are that the log of 1 is 0. So when x is 1, y is always 0. And the log b of b is 1. So when I get to x equals b, y is 1. Now I got to apply that to this thing here. I know what my base is, but I got this x plus 2 to worry about also. It's a horizontal shift if you're into the transformations. But I'm going to think this through for this one. Log of 1 is 0. So if x is negative 1, that's when I have the log of 1 right here. So it's negative 1, 0. So when x is negative 2, you get the log of 1, which is 0. That's good. When that input is b is 1/3, I'm going to get 1. Well, that happens when x plus 2 is 1/3. So that happens when x is negative. What's that? 1/3 minus 2. Negative 5/3. When x is negative 5/3, I'm going to get the log base 1/3 of 1/3, which is 1. So those 2 points would be on the graph of it. Let's see what we get from those. We know from the domain, this thing stops at negative 2. When x is negative 1, we get 0. And when x is negative 5/3, we get 1. That's actually down here. Negative 5/3 is almost to negative 2. It's going up to 1. So it looks like this one goes up. And then it's going to come through here. Line out this direction. Now, if I want to check another point on that, I'm trying to review. So I like the looks of that graph, but I'm trying to review some stuff. So I want to think about how would I check that if I'm doing that. If I want to see what happens with this thing, I'd like to see another point out here and see if this is kind of on the right track or not. So what happens if I just pick an x value and plug it in right here? I want to get the y that goes with it. Well, it's a function. I can plug in different inputs. So I want to do log base 1/3 of 7 plus 2, which is 9. I happen to pick a nice number on that, but I'm going to calculate that a couple of different ways. One thing to remember, I'm trying to review this stuff and get through the basic properties. One thing to remember, when you have log weird base of something, we can rewrite it using the change of base thing. You just do regular log of this, and then you divide it by the log of the old base. So one way to do this is log of 9 on the calculator divided by log of 1/3. So let me see what that comes up to. Regular log of 9 divided by regular log of 1/3. That's what I want to do for a calculation. That's what I have after the change of base formula. So that comes out to negative 2. Hey, that's a nice number. That looks kind of right with my graph here that I'd be down here at 7, negative 2. So that looks good. But also let me think about why that came out to a nice number. If I can write this expression in terms of that base, then I can do this. I'm looking for the y that's equal to that. And if you just write it in exponential form, this log statement can be turned around into exponential form. If it's base 1/3, then the base is 1/3. The input into the exponential is the output from here. And this is the output from that one. So 1/3 to what power equals 9? That's exactly what I'm asking when I say log base 1/3 of 9. Is what power do I put on 1/3 to end up as 9? And we got to square it and we got to flip it. So that's a negative 2. 1/3 squared is 1/9. So 1/3 to the negative 2 would flip that over and become positive 9. So negative 2 makes sense as the y value right there. That looks good with what the calculator is saying. That checked it out okay. And gave us a chance to remember how to change from log form to exponential form. Going back and forth between those two forms helped us sort this stuff out a lot. So that's one of the things we did on the log exam there. Doesn't look like a regular logarithm graph, but that's because of that base being small. Like that log graphs with the base less than 1 are kind of flipped over like this one. That's an odd example. But key ideas to remember there. The 2 key points for the log graph. You should remember those when it comes to log graphs. You should remember the domain thing that whatever you're taking the log of has to be greater than 0, and how to switch back and forth between these forms. And then also this kind of idea about, I mentioned horizontal shift. Instead of just x in there, I have an x plus 2. That shifted the graph 2 places over to the left from where it would have normally been. So those graph transformations we messed with a little bit. Those are useful on logarithms and every other kind of graph. Those are good things to remember. Not really wanting to get back into trig now because we just took a test on that. I'm hoping people are in pretty good shape on those. I want to look at some of the older stuff. So this is number 26 from the review. Gives you a couple of function definitions here. For this problem, f of x is 2x minus 1, and g of x is 3x plus 7. You want to be comfortable with function notation now after seeing log functions and trig functions and okay, that was about it. Exponential functions. After seeing those, remember, even basic things like this can be written as functions, and we should get used to the notation. This one's asking us to find fg of x. It's written with parentheses around it, but that's just fg, no symbol between them. That means to multiply. This is not a composition. This is multiplying those two things. I kind of want to remember what both of those things were. So I mentioned composition. I also want to do this just so we remember how this goes also. So that's not part of the review question, but the distinction between these two things is important. We're going to do both so we can see the difference. Fg of x means f times g of x. It just means multiply the functions. So it's just doing this multiplication. 2x minus 1 times 3x plus 7. That's an expression for the function. That's the expression for this function. F times g just means multiply those expressions. So that's doing a little polynomial multiplying. Hopefully, familiar idea. Simplifies a little bit. I got 6x squared plus 11x minus 7. That's the product of the two. That's the answer to that one. F circle g of x is not talking about multiplying. That's talking about what happens when you compose these two functions. You should read it f of g of x. You should write it f of g of x. Then that's what that circle thing means, is there's an inside function plugged into the other one. So that means we want to do f of whatever g of x is, 3x plus 7. So that means taking that whole thing, substituting it into the f function. F of x is 2x minus 1. So f of this thing is 2 times this thing minus 1. So can simplify a little bit there, but that's the expression you get from the composition there. It's just 6x plus 14 minus 1. 6x plus 13 is f of g of x. Very different from the multiplying result. Different thing going on. Domain for each of those functions would have been from minus infinity to infinity, because that's just they're just linear functions. No problems with domain on that.
Oh, yeah. Sorry, it takes me a moment.
We do a little bit with inequalities. I want you all to remember inequalities. That's one of these things on the practice has to do with inequalities. I'm going to do a simpler inequality first, and then we'll do. Well, they're both pretty simple. The one on the practice is pretty simple also. Remember how to think about inequalities. And how to write the answers here, that's really the interesting part for inequality. So you got a less than or a greater than thing going on. You might have something like 5x plus 2. Instead of an equals, I got a less than, and then I got terms over here. So 8x minus 1. Where is 5x plus 2 less than 8x minus 1? I'm going to basically solve for x in this thing, and I'm going to think about which side of this is true. So 2 ways to think about this.
Yeah. Okay.
That would both work. I'm going to solve it both ways.
Okay.
If I just work with the inequality, I have to remember how the symbol goes at each step. I want to get the x terms on one side, so I'm subtracting 8x from both sides. If I subtract stuff from both sides, it doesn't change the inequality because this thing would still be bigger, or this thing would still be bigger. I just moved them down by the same amount. So when you're doing adding and subtracting, the inequality stays the same. So subtracting 2, the inequality stays the same. I can work this down to solve for x that way. Nothing different. But at this stage, I have to remember what happens differently. Dividing by a negative, multiplying or dividing by a negative is going to change things around. So the result is going to be the other way around. It's x greater than 1 is when that's going to be true. So the other way of thinking about that I mentioned is just to think, let's not worry about the inequality all along. Let's go over to equation land and find the solution to the equation where these things are equal. And then I'm going to go through those steps with normal equation stuff. I get the same steps over here, except I get x equals 1 is the place where they're equal. That's where it's going to change. The inequality is going to change from true to false. So I could just think about that on the number line. Here's a 1. If I take any number bigger than that and plug it in here, what happens? So any number bigger than that, I'm going to find out this is true. If I take any number smaller than that, like 0, that's over on this side, I'm going to find out this is false. So it ends up true on one side and false on the other. That's typically what goes on there. And then I can see the graph of exactly where this is true. The solution to the inequality is where x is greater than 1, or the interval from 1 to infinity. Actually shouldn't have the square bracket there because it doesn't include 1. X has to be greater than 1. So I really should write it this way. The interval from 1 to infinity, not including 1. There's a circle equation. We talked a little bit about those here a minute ago, but there's some more complicated inequality that goes with it. Number 13 in the review. More complicated inequality, and it gives us some more factoring practice, which doesn't hurt either. So number 13, x cubed plus 3x squared minus 9x is less than or equal to 27. It says to write the solution in interval form. Interval notation, that's what we used on the last one. From something to something, or from something to infinity, those kind of things are intervals. That's the notation we want the answer for. Something like this, you're not going to just get x by itself by pushing things around with normal steps. This is a polynomial equation. We're going to have to factor and use the zero factor property. And that really only works for equations. We can't really break down inequalities that way. We have to do it by going over to equation form, finding where it's equal, and putting those on the number line. We're going to come back to a number line and find out where it's true or false on the number line, what my intervals are. So that's the thought process when we get more complicated inequalities. Make an equation, work the equation. Then your solutions are where it changes from true to false. We have to come back and think through the intervals. So where's this equation true? Now I got a little bit less to think about. It's just a regular equation now, but it's got powers in it. So I'm going to have to solve that by the zero factor property. It powers in it, but it includes an x cubed, so it's not even a quadratic thing. It's really bigger. I'm going to have to factor it. So I need the zero. I'm going to do zero factor property on this. So I need the zero. I need to do the minus 27. X cubed plus 3x squared minus 9x minus 27 equals 0. It gets the 0 on one side. And then I got to factor that thing there. This is a 4-term factoring problem. So I'm going to go off to the side and try to find the factors of this thing I'm asking this. I don't have a GCF to pull out. There's nothing in common with all 4 of them. But it's a 4-term factoring problem. So one way of setting those up is drop them right into here and see what happens. Your 4 terms go right into the box. Minus 9x minus 27. That's kind of nice. And then pull out your factors if you can from here. So from this column, you have an x in common. From this column, you have a 3 in common. The negatives are along a row, so we'll use a minus. 9 is the common factor for that row. And x squared is the common factor from this row. So I got those factors. X plus 3 and x squared minus 9. Just great review problem because it goes through a lot of the steps that we did. So factoring a 4-term problem. Now it's factoring a 2-term problem. I still have an x squared. I should be asking myself, can I factor this further? And I can. Even if I don't, I'm going to have to think about it here. Suppose I just left that unfactored. The property says I got to solve for where x plus 3 is equal to 0, or where x squared minus 9 is equal to 0. At some point, I got to work out the 2 things here. If I don't factor it, I can do square root property. But it's where x squared equals 9, so it is plus or minus 3. That's the answers to that. So we got positive 3, negative 3, negative 3 again. So I only ended up those 2 solutions. Negative 3 and 3 are the x values that were back to the number line to think about the inequality. So negative 3 and 3 are where these 2 things are equal. I got to see whether it's true in between there or what. So I'm going to check these things this way. If I take some number out here like negative 4 and substitute it in here, does it come out less than 27? So negative 4 to the third plus 3 times negative 4 squared minus 9 times negative 4. Bunch of calculation to do. I just wrote it down. I'm going to do it on paper. You could also do this in the calculator. Be careful with your parentheses because that's a negative value with powers on it. That can throw things off. But that should come out minus, plus, if you handle your signs right. So it ends up being positive 20. 84 minus 64 is positive 20. Comes out to 20, which is less than or equal to 27. True. So I got a true value there. So everything on this side is true. And then let's see what happens in between here. So a different number somewhere in between negative 3 and 3. I can use 0. That's an easy number to do calculations with. So I plug 0 into that same process. And I'm going to see what happens with that. Well, it all comes out to 0. That's still less than or equal to 27, isn't it? So we're still true. So it's still true in between there. We got true in that interval. We got true in this interval. 3 is another solution to the equation, so it might change at 3. We got to see what happens on this side. So let me do something out here like positive 5. Same function. different input. That's 125 plus 75 minus 45 is 155. That's not less than or equal to 27. No, that's false. That's not true. So we got false on that interval. That's where it stops being true. It's at 3. I really should check. I'm not going to take the time for it now. I really should check what happens at those points. Well, wait a minute. I know what happens at those points. That's where it came out equal to 27. Those were the solutions to the equation, the points where this expression came out equal to 27. That's true because it says less than or equal to. So I already know it's true at those points. So it's going to include the 3. It's true all the way from negative infinity up to 3, and then it stops. It's just that interval that's my solution, including the 3. That's where it's equal. Quite a bit to remember there. So these practice questions should bring up a lot of memories for you. Things you might have to take a little time and look back up because it's been a little while. Hopefully it seems familiar now at least, and I expect you probably get stuck on some things as you go along, so I'm expecting to get some questions on that. I haven't I held off on answer key for that thing. I sent you a bunch of questions without any answers. I think I have an answer key for it ready to go, but I wanted to send that out later because I want people to try stuff out, and then if you go back through it, try to remember stuff. That's healthy. And then if you go back and check your answers, you get another repetition of looking at the material, and then you can sort out the ones that you may have made a mistake on or not remembered how to do. So I'm trying to get people to go through that process a couple of times. So I am going to send the answer key out, but that'll probably be a part of Monday's announcement because we're doing final exam review into next week. So I will have one more Monday announcement like usual. That was supposed to be our last class day. And then the final exams are scheduled for the 6th and 7th next week. And this final is scheduled for the 6th at 8 o'clock in the morning. So we can get this thing done. The 6th at 8 a.m. Trying to do a 4-hour block for that. So if you're available from 8 to 12, great. We'll take the final then. If that time is conflicting with something else for you, let me know. Because I do have other finals that on the 6th and 7th, I can fit you into one of the other times. So send me an email if the 6th isn't going to work. Otherwise, I'll send it out to those of you that are working along on this early in the morning on the 6th. Well, more to come on that. I will have the announcement out Monday to talk about what's going on with the final. And I'll have the times and stuff included in that, and I will put up the answer key to these practice problems then. So if you try some of these things out, and you'll be able to check your answers there before we get to time for the final. So I hope that's going well for people. Remaining questions that you have from the trigonometry or from any of these sections, really just get the questions to me, and I'll get back to you either by email or I'll put something out. So let me know where I can help. I will get that answer key out with the assignment Monday. Work through these practice problems between now and then. And let me know what you're having a hard time with.
I don't know what it is about chocolate and peanut butter.
There's links in the announcement from this Monday on the
Chocolate and peanut butter.
now the Lumen stuff that you can look at as practice also. So those are available. I'll be in touch.